Hey guys, what's up? So super frustrating. I recorded a 20-minute video and now I can't access any of it. But for you, no problem. Just watch this video and hopefully this one works. So energy, that's what this revision session is all about. This is a fundamental concept in physics. But what actually is it? Well, energy is the ability to do work. So in any of these situations where you've got something moving, you've got work being done because energy is put in to cause that work to happen. Okay, and we'll look at what the system means in a minute. Now, here's a really great exam tip. The work done is always equal to the energy in whatever situation that is. So we'll get on to that in a second. But whenever you've got energy transferring from one form into another form, you've got that energy is going to be equal, and that is the work done in the system. So what is a system? Well, a system is just an object or group of objects. So for example, if this is a ball and it goes up in the air and then it comes back down, that's one system. So the ball is a system. Okay, so my handy lights here that are going to turn on and off during the video. So that system is keeping all of the energy in one place. Lots of different examples there of different systems where you've got energy changing. So work done, there's a calculation for this. We use the letter S, sometimes we use the letter D to represent distance. You just need to multiply these two things together. So the farther something moves, the more work you had to do. The more force you had to push on that object, well, the more work was done as well. When you do work, you're actually using energy. So that's why the units for work done is joules, because joules is the units of energy. The force is in newtons, and the distance will be in meters. The first type of energy I want you to think about is gravitational potential energy. So the way that we note that here, energy is the big E, and then we do a little subscript P. That just means potential. So energy will always be an E, and the P is there for potential. So for gravitational potential energy, we need to multiply these three things together. The mass, the gravitational field strength, and the vertical height that the object is at. So for any object that's raised up into the air, like my remote, it has gravitational potential energy that can be transferred to kinetic energy. And I had to do work to raise that object. It took me some energy to do it. So that energy is stored, potentially, in that raised object's height. Now, if you don't know the mass, but you do know the weight, then you may remember that the weight is actually the force of gravity multiplied by the mass. And that gives you the weight in newtons. Okay? So for example, that box there, 10 kilograms, it will have a weight of 98 newtons on the Earth because the force of gravity is 9.8, or the gravitational field strength rather is 9.8. So you'd multiply that together, that gives you 98 newtons. Well, the force of gravity is obviously stronger, or weaker, sorry, on the moon, so it would be a smaller number that you're multiplying by. Okay, so you would only get 16 newtons on that there. Okay, so the same box would have a different weight because mass and weight are not the same thing. But what's interesting here is if you take the weight as newtons, okay, you can actually get this same equation and transfer it over there to energy. The gravitational energy would be the force of the weight in newtons, and you multiply that times the height. So this equation is exactly the same as that one. We've just already multiplied mass and the gravitational field strength, and that's how you get the weight times the height, right? Now look at this here. Joules equals newtons times meters. Is that familiar? Should be. Look at work done. Joules equals newtons times meters. So that's quite interesting. To get the gravitational potential energy here, it's exactly the same equation as for work done. So when I do work to raise this object up, the distance that I've moved it, the height that I've moved it at, multiplied by the force that I had to pull it up by, that's the same thing as the energy that's then stored in that object. That's just quite interesting, might help you to remember those equations. Okay, for kinetic energy, that's an object that's moving. I might like to see this actually as an E with a little K there. And that would tell me, so I'll rub this one out. That would tell me that this is energy. Oh, it's gone now. Anyway, That's energy for kinetic. How do you multiply that out? Well, this is a little bit confusing, right? So 1/2 mv2, what does that mean? Well, when you multiply it out, you would do 0.5 multiplied by the mass and multiplied by the speed squared. Okay, so speed, we put that as v, or velocity is another one. Okay, so in your calculator, you'd multiply 0.5 times by whatever the mass is, 5 kilograms, times by whatever the speed is. Okay, but make sure that you square the speed before you do anything else. So if it's moving at 5 meters per second, times it by itself, that would give you 25, and then times it by the mass, then times 1/2. That gives you the energy stored in any object that's moving. Now, elastic energy is another store of energy. So for example, when you pull on I always get this word wrong, on a spring, when you pull on a spring or on a rubber band, yeah, you're actually having to do work because you have to apply a force to move that distance. So work is done on a spring that's stretched, or on like a sponge or something. If you squash it, that's compression. So either way, that will allow the energy to be stored up in that object, and then the energy can be released to move it back to its original position, as long as it hasn't exceeded that limit. Have you ever seen like a hair bubble that's been stretched too far, or a rubber band? If it's pulled too far, it actually goes all slack and loose. Well, then it's not going to return to its original position. Obviously, that's lost the elastic properties. Okay, so it no longer returns to its original shape. Here's the equation that you use to calculate elastic potential energy. That's super interesting because look, energy equals 1/2 times something squared. Is that familiar? It should be. Look at this. Energy equals 1/2 times something squared. So that's quite cool. You can remember this one for elastic energy. It's exact same equation. It's just got different values, different variable and different constant. So for kinetic energy, we had the mass. That's the constant. So a car, regardless of how fast it's moving, it's always going to have that same mass, right? But the speed is what might change. For a spring, it always has what's called the spring constant, but the extension changes. Now, what do I mean by that? Well, the extension of a spring is how far I've stretched it. So if it started at 3 centimeters and I pull on it until it gets to 9 centimeters, well, then the extension is 9 minus 3, 6 centimeters. So if you were working out how much energy you've stored in that spring, the question would need to give you the spring constant. Let's say it's 2 newtons per meter. And then you would multiply that by your 6 centimeters, but you'd square that number. So 6 times 6 is 36. You times it by the spring constant. 2 would give you 72. Then you would times it by 0.5, and that would be back to 36. So the energy in that would be 36 joules. And you have to assume the limit of proportionality hasn't been exceeded. That's this one here. Okay, if the spring breaks, then it's over. I got the power. What do you mean? Watts, the units of power. That's literally it. Watts is the units of power. So W means watts, joules is for energy, and seconds is for time. So power is the rate of energy transfer. I'm a runner, but I run slow. So I can't transfer energy as quickly as someone who's a sprinter. I like to do the long runs. So my times are bigger, even if I'm putting in lots of work, because I'm transferring lots of energy, but my times are much, much higher. Now, somebody who does a sprint, they're maybe not putting in as much work as me, but because they do it so quickly, they are actually much, much more powerful. And that's reflected in the size of their muscles. So a sprinter would always have really, really big, strong legs. And you see the distance runners, even Olympic athletes, the elite runners, they're always quite thin people. Okay? And they're doing more work, but it's over a much, much longer time. So the rate is lower. Now, whenever you transfer energy, that energy is going to be transferred usefully, or it can dissipate, but it can't be created or destroyed. That's the law of conservation of energy. There can't be any overall net change to the energy. What does that mean? Well, dissipated energy, think about that like energy spreading out. Okay, so when you're in the classroom, you're all concentrated together. when you go out on the field, you're all dissipated. It's hard for somebody to teach you, right? Because you're like everywhere. So when the energy is really close together, it's more useful. So when it's dissipated, it's tough. Usually what's happening is that's spreading out through the thermal energy transfers. So if you want to reduce unwanted energy transfers, you're usually going to use insulation to keep heat in one place, or you would use lubrication if it's like parts that are moving. Like my car's engine, I've got to make sure it has motor oil so that those moving parts don't get too hot from the friction. Okay, that will increase the efficiency as well. Now, thermal conductivity, when you look at the rate of cooling of a building, that's the rate of energy transfer from the thermal energy. So something like a hat, like a winter hat, that's got a low thermal conductivity. So that's going to help you to stay warm. It's going to trap that heat in there. Imagine that you could put a hat around your house. You wouldn't have to pay as much to heat your house because you would be keeping all of that energy in. Okay, so the rate of cooling of the building is affected by the thickness of the walls and the thermal conductivity of the walls. That's why we put insulation, fiberglass insulation in the walls. Now here's an interesting picture here. This is like a pendulum. So this is like a ball on the end of a string that's swinging back and forth. Okay, now at the high point of the swing, when it swings up to its highest point, that's the maximum gravitational energy, but it's the minimum kinetic energy, because what happens when it gets to the top? Stops, right? If it's not moving, stopped, zero kinetic energy. When is it moving the fastest? It's actually right down at the bottom when the gravitational energy is the lowest. All of the gravitational energy is transferred to the kinetic energy, so that's the maximum down there. And then it goes back up to the top again, goes back and forth. Okay, so those energy transfers, that should be equal, assuming that there's no energy loss in the system, assuming there's no dissipation of energy. We know that's never going to happen in reality, but in questions it makes it a lot easier to answer if we assume that. So thinking about the energy transfers, you get some useful ones. For example, in a wind turbine, these are generating electricity for us as they spin. So the wind is moving, that's the kinetic energy, and they capture that and transfer it into electrical energy. Okay, what about in a radio? Well, it could use some of that electrical energy from the kinetic, from the wind turbine. You want it to produce sound, it's going to produce some sound waves. Those are actually still a transfer rather than a store of energy. But it's also going to release some energy as heat waves. It's going to increase the thermal energy of the surroundings. So underneath the radio, you'll notice that the desk gets warmer. You probably won't notice, but the air particles are getting very slightly warmer as well. Okay, so that is not a useful transfer. That we would say is wasted energy. Okay, so we want to know how much of the energy is usefully transferred and how much of it gets wasted. For it to be more efficient, you want to transfer more to those useful transfers. Now, when you're doing these calculations, exam tip is always make sure you take the smaller number and divide it by the larger number. Okay, because you want to end up with a decimal, then you can multiply it by 100 to get it as the efficiency. So let's just take an example here. If I asked you to work out the efficiency of that radio, and I said I put 100 joules, or let's make it more difficult, I put 20 joules of energy into the radio, and 5 joules of energy is transferred out as sound. Well, that would be useful, would be 5, and 20 would be the input. So it would be 5 over 20, that's 1 over 4, so that's 0.25 multiplied by 100%, that's 25% efficient. You can actually do the exact same thing with power if they gave it to you in watts, same equation, no problem. Now, I talked a little bit about this as well, but it's worth mentioning for appliances that sometimes you want to increase the efficiency of your appliances, means you've got to increase the amount of useful energy being made. And you also want to be reducing energy that's wasted by the resistance of those devices. So in a light bulb, for instance, an incandescent bulb is going to be a lot hotter than an LED. You probably noticed that before. LEDs, light emitting diodes, they never really get hot, so those are really energy saving bulbs. They have a higher efficiency because they have a lower electrical resistance. So less of the energy gets transferred to the heat store of the bulb itself and to the heat store of the particles around it, so less energy is being dissipated to the surroundings. more of the energy, a greater proportion is being transferred to the useful energy outputs. Okay, that's the key there. And I said about reducing friction before as well. When you say smaller contact surface, think about an ice skate gliding over the ice. It's a very, very thin contact surface on the ice, on the blade of the skate. Whereas if you were to try to slide with your shoes, yeah, you could probably skid with your shoes on ice because there's low friction anyway, but you definitely wouldn't go as far as you could go if you were on an ice skate. Okay, and reducing heat loss is the key thing for increasing the efficiency of a device. Now, when you talk about energy resources, this is a completely different concept. Okay, energy resources, when you get renewables and non-renewables, these are ways of generating electricity. So we call them resources because they are good sources for us to get electricity from. They're not the 8 stores of energy that we are talking about with like kinetic and all that stuff. These ones here, we're using the kinetic energy of the stuff, or we're using the thermal energy, or we're using the chemical energy in the system, and we're transferring that electrically to our other devices, our computers, our laptops, phones, whatever it is. Okay? So these are energy resources. You have renewable kinds and non-renewable kinds. Now, if I use a barrel of oil, for instance, fossil fuels, and I burn that, then tomorrow I can come back and use that same barrel again. Okay, so I can generate electricity by burning oil. I burn the oil, I heat up some water, it creates steam, steam turns the turbine, and that turbine will turn an electrical generator. And I get electricity out, yeah? If I go again to use that tomorrow, the barrel's already empty, I can't use it again. The barrel's gone. I can go get a new barrel, but the barrel's not going to be replenished. So I can't use that again. But with the sun, if I use solar energy today, there's still sun again tomorrow. Now, today it's already dark outside, and tomorrow it might not be sunny. But you know there's going to be more the day after that. So these ones here, those ones automatically replenish. That's why they're called renewable. The non-renewables, it's a fuel or it's something that's being burned or used. Even if it's a nuclear resource, it's still being used up. Okay, so why do people use these if there's all that negative environmental impact from the burning fossil fuels with the greenhouse gases, ruining climate, ruining habitats for things? Well, generally, it's because they're cheaper and they're more reliable than the renewables are. We're trying to find really great ways to make renewables more reliable and to make them more concentrated so that we can use them for less amounts of money. But if you have like a really poor population and you need energy really quick, then obviously you're going to just try to provide energy as quickly and as easily as you can. And that's where we come into conflict between developed countries like the UK and developing countries like Brazil or India, Pakistan, places like that. They don't really care as much about the environment, and you got to understand that because they don't have as much money as we do. We got money to use on stuff, so they're not in the same situation as us. Now, there is a required practical about specific heat capacity. This is a change in thermal energy. What I'd like to do is just to remind you that thermal energy and temperature are not the same thing. Just remember the example I always give in lesson. If you go to the beach at the end of a hot sunny day, which one's going to be hotter, the sand or the water? Obviously, the sand is much hotter. Why? Because the water has a much greater specific heat capacity. So even though they're absorbing the same amount of energy throughout the day, the water, the temperature is not changing as much because it takes a lot more energy to increase the temperature of that water. So you cool your feet off in the water if your little toes are getting burned on the sand, right? That's because of the specific heat capacity. So the specific heat capacity is just how much energy is required to raise the temperature of a substance. You got to make sure you're talking about 1 kilogram and 1 degree Celsius, otherwise it's not standardized, okay? This is the required practical. You use a voltmeter and an ammeter so that you can work out the energy, and you multiply that by the time that power, you use those two, it gives you the power. You multiply that by the time that gives you the energy. If you use a block, you just measure the mass of the block and measure the temperature at the start and the end. That gives you the temperature change. And using that, you can work out the specific heat capacity for any material. if you plot the temperature against the work done, okay, so if you measure it every single minute, then you get a running graph there. You can just calculate the gradient, which is the temperature change versus the work done, and pardon me, that will give you the specific heat capacity. Okay, if you were doing physics as separate science, you do need to know about the insulation required practical. What we do for that one is you get a beaker of hot water and you wrap it with newspaper. So you might get like 5 different beakers, and one beaker, so the green one there, the beaker 1, you might wrap in 0 newspaper, and beaker 2, you might wrap like 5 times in newspaper, and beaker 3 you wrap, say, in 10 times. So wrap the newspaper around 10 times. And you keep a few things the same, like keep the same cardboard lid, keep the same volume of water, make sure the water is starting at the same temperature, record the temperature over time. What you would expect to find is if I change the thickness of insulation, it should have an effect on how long it takes for the material to cool down. In other words, the rate of cooling. So if you plot cooling curves for all 3 of those, then you'll see the dependent variable, the temperature change in those beakers, they will be different, assuming you've done everything else really well and controlled those. Okay? You can go ahead now and join the Teams meeting now that you've watched the prep video. So jump onto the Teams meeting, watch the walkthrough of some exam questions. I'm going to talk through some exam questions on Teams, and make sure that you're asking and getting your questions answered. You'll also find on Teams that you can find the file for the other exam questions that I want you to have a go at. Okay, so have a go at the file. I forget what it's called, something about exam questions. There's a file in that Teams thing. So find the button for files, and then you should find there's a PowerPoint. I just suggest that you present that, because otherwise the questions are already answered. So if you watch it in presentation mode, then you can sort of have it on your laptop or whatever, and then just like have a go at answering the questions before you see the answer pop up. Okay, hopefully that makes sense. If you don't get what I'm saying, then just ask me on Teams. Okay, I'll see you guys on Teams.